Hi, I'm Uriel, and I go to the City College of New York, and this is a project on advanced mechatronics and how it applies to exoskeleton modeling. So, robotics or mechatronics is a branch of science that includes mechanical engineering, electrical engineering, computer science, and robotics deal with the design, construction, and operation, as well as computer system for their control, sensory feedback, and information processing. For my project, I'm going to be comparing two different types of actuator, the Quasi Direct Drive and the Series Elastic Actuator. And the way I'm going to compare them is by looking at the back drivability and the bandwidth, and also processing this with the robotic control and using Simulink. So the difference, so an actuator is powered by a motor and converts it into an electrical energy it converts electrical energy into a mechanical torque. Um, when it comes to an series elastic actuator, the difference component is that it uses an elastic element, um, while a quasi direct actuator eliminates the need of physical strength. When it comes to human exoskeleton, there's three major components: the actuator itself, the transmission, and the wearable structure. Um, the actuator has an electronical part and a mechanical part. This is a transmissional part, and the wearable structure should be comfortable for the person to be wearing in a long period of time. When you use Simulink, it is able to calculate this by using the transfer function, and these are the different types of components that are embedded in each of them. When it comes to comparing the actuator to human motion, the Series Elastic Actuator is a little bit more relatable to the human, while the Quasi Direct Drive Motor Actuator it's a little bit more proficient in performing compared to the bandwidth when it's able to react much quicker than a human can. As how I said before, the Series Elastic Actuator has a spring in it and normally has high gear ratio transmission, while the Quasi Direct Drive Actuator has low gear ratio and doesn't have a spring, which makes it have a larger torque. Is able to produce larger torques. This is a control diagram. It takes an input that goes through the computer controller and gives voltage to an actuator, and then to a gear or robot, and then the sensor feeds back into the controller. This is a control block diagram that I use to calculate the back drivability simulation and the bandwidth. So the difference between the two of them is that bandwidth measures how fast it responds to changing output, while bandwidth is the level of easiness of transmission from output axis to input axis of movement. So back drivability is basically how low resistance it is to apply force. And these are the parameters that I use. As you can tell, the QDD actuator actually has a gear ratio of 8:1, while the Series Elastic Actuator has 100:1. When I calculated my results using Simulink, I was able to calculate the CEA actuator has a resistant torque of 2.9, which is not that bad, while the QDD actuator has a resistant torque of 0.39, which is pretty great. Has very low resistance to try to move the actuator. The series, as stated earlier, you calculate this at negative decibel, and the SEA actuator had a 4.9 hertz bandwidth, which is pretty good and responsive, while the QDD actually had a very impressive higher at 113 hertz, which is pretty great. There's a little video of how these exoskeleton are applied in the real world. This is a little short video of a guy wearing an exoskeleton, and is he able to perform his normal work tasks as usual, just wearing these improvements to his body. So, summary of what I learned. A summary about the presentation is that simulants compare real-time system simulations between hardware and software. QDD actuator are more efficient both in mechanical and electrical components compared to the SEA actuator. QDD perform better because they have a large torque motor and smaller gear ratio. The drawback of the SEA actuator is that they do have springs and it dampens the amount of torque that they're able to provide. And also the bandwidth is lower. Other things that I learned in the class, I learned a lot of many other things such as soft robotics, data structure, communication protocols, power electronics, closed loop system, just as the one that we're using here with a sensor, motor model, an encoder, PID control, actuators, just as this one, and other robotics control. I want to give thanks to all the resources that I was provided, which was papers, the lectures, and all the articles. Once again, thank you. My name is Uriel.